Do you want to make your own PET filament at home? If so, you're at the perfect place. In this video, we are not only going to build this amazing machine, but we will also be building this nice circuit. And I will be sharing all of it as open source. If you are interested, let's get started. Before starting, I simply want to explain how the machine works. First, we are going to cut our bottle into a small PET strip. Then we pass that strip inside our hot end, which is an aluminum block with a heater and a thermistor attached to it for reading the temperature. After that, we pull the strip with the help of our motor at a constant speed and temperature, which we adjust from our menu. And that's pretty much it. Then we can feed the filament into our 3D printer and print whatever we like. I think you got the main idea now. So let's move on to assembly. As we assemble the machine, I'll point out important things you may need to pay attention to while working on your own. If you are facing any difficulties, you can click on the part you want to skip to, but I highly recommend watching the whole video. First, let's start assembling the main body of the machine, which will be our Sigma profiles. I saw many creators using wood for this, but I want to make it a little more professional and reliable. We start by assembling our Sigma profiles like this. You'll be seeing all the materials on the screen as we assemble, but I will also write them down in the video description, so you can check them there as well. Also, don't forget to add these T-nuts here. As we move on, we will use them to mount our stepper. By the way, you can find the link in the description for these 3D printed T-nuts. I highly recommend using this Allen head bolts since the Allen keys are much better at reaching tight spaces. I only have 5 and 10mm bolts, and 5mm is too short while 10mm is too long for nearly everything in this build, so you'll see me using some washers or extra nuts on 10mm bolts through the whole video. Sorry about that. Well, the assembled profiles look like this, and I really want to thank the person who invented these Sigma profiles. They are super useful. After all that, I just simply assemble the motor to our motor mount with these plastic bolts, but don't tighten them too much, since we'll be moving our motor back and forth. The reason we are using this NEMA 17 step motor is that it's easy to control and provides high torque at low speeds. But this 0.4 Nm torque won't be enough for our project. So that's why we are using these gears. This gearbox has a ratio of around 16:1, so our torque will be 16 times higher. After that, I assemble our NEMA 17 to the Sigma profiles just like this. Now we can continue to the assembling the gears. We will be using these M3 bolts to keep our bearing in place. And we will also use these bushings since the M4 bolt is not going to fit to the bearing. If it's your first time putting all of this together, it will be a little hard to pass the bolt through the gear. So you can wear some gloves to increase your grip. After the middle gear is installed, it should look like this. As you can see, we can make or break the contact by simply moving the stepper to the side. This gear has a little play because of the center of the bearing, but it won't cause any issues as we move on. Now let's assemble all 4 feet. As you can see, they are looking pretty good. After that, we can continue assembling the main gear. It is made up of 2 parts. We simply attach them like this. And then put our last 2 bearings like this. In my case, they fit perfectly. I also added this piece to the files, so you don't need to print everything to test the fit. You can just print this bearing fit piece, then modify the files according to your needs. The same bushing situation applies here too. Just attach the bushings, then attach the main gear like this. We are using 3D printed bushings, but they fit pretty well. As you can see, there is little to no play. And just like that, I'm attaching the main wheel to the base. And again, it looks super cool. As you can see, when I move the motor, all of gears move as well. Perfect. It fits so well that I nearly forgot to bolt it to the profiles. I think this is a great time to jump onto the circuit. Let's just talk a little bit about components and the circuit schematic. We are using the STM32 F051 as the brain of our circuit, a nice and powerful MCU with an easy to solder package. Other than that, I decided to use this 240 by 240 OLED screen and paired it with a nice rotary encoder, so we can use the menu effectively. As for the power input, I thought people might want to build it either 12 volt or 24 volt systems, so we are using a small and efficient buck converter. We also have a 4 amp resettable fuse at the input, so we'll be safe from short circuits, and with this TVS diode, we'll also be protected from high voltage spikes. Other than that, here you can see the A4988 stepper driver we use to drive the motor. I used these switches to select the micro stepping mode, as people may want to adjust it later, but in my case I'll be using 1 divided by 16 micro stepping, so they are all in one direction. And here you can see our limit switch input. If the filament runs out, it will trigger and stop the machine. Just beside it is our thermistor input, where we will be reading the temperature. Okay, you are probably going to get angry at me because everything else is easy to solder, except this MOSFET here, which is controlling our heater. It can handle up to 5 amps, which is way more than enough for my 12 volt 30 watt heater. Other than all of these, we have one buzzer for feedback and a programming input for the ST-Link, and that's it. The circuit is pretty simple. Now I want to give a little more information about the circuit. If you don't want to hear the technical details, you can skip to here. The things I paid attention to while designing the circuit are, as you can see, the crystals and the decoupling capacitors are very close to the MCU. All of the PCB tracks are thick as they can be, so they will have less resistance. Also, the thermistor input is an analog input, so it can easily pick up parasitic noise, which is why it is short as possible and placed far away from noise generating components, such as the buck converter and the stepper driver. For the buck regulator, it is important to keep the distance as short as possible between the regulator, inductor, and capacitors. So that's exactly what I did here. I also hate circuits with sharp corners, so I rounded them to fit perfectly with my mounting holes. And of course, let's not forget the via stitching all around the circuit. Having a good ground reference is always best, and that's why we are using a 4-layer PCB with the 2 middle layers acting as ground planes without any signal traces. Okay, now it is time to order the circuit from our sponsor NextPCB. For that, I extracted the Gerber files and opened NextPCB's website. Then uploaded our Gerber files. As you can see, there are many options here. We are going with 10 pieces and blue solder mask, which will look pretty good with our OLED screen. After that, I added it to the cart and ordered the PCB. And as you can see, they arrived perfectly. Very professional looking and great quality. Thanks a lot to the NextPCB for sponsoring this video. Now we can get to the soldering. I applied solder paste to all of our pads and then soldered the components. Two very important things I want to mention. Here you can see I marked the negative input, so be careful when connecting the power. The other thing is that I also marked the enable pin on our stepper driver. You have to pay attention to the orientation of the stepper driver, or you are going to destroy it. Before uploading the first code, I connected the power and a step motor to adjust the current limiting setting on our stepper. We can do that by turning this potentiometer and reading the voltage value. A higher number means higher current. Mine is adjusted to 0.7 volts, which should be more than enough in our case. And I am not going to go into too much detail, so let's continue. After assembling the circuit, I wrote the code for it and tested it a lot. But I decided to tell you about the code when we are done assembling the machine, so let's continue. Now let's assemble the power supply. As you can see, I crimped some ring connectors at the end of our power supply cable so it will hold better. This part is very dangerous, so please do it at your own risk. And also make sure to use a power cable with a ground connection. I want to be sure the whole body is grounded, so I will also be connecting a ground wire to the Sigma profiles using a metal T-nut. After securing the cable to our power supply, I also attached the two cables that provide power to our PCB. After that, I used these 4 3D printed parts to attach the power supply to our machine. And it looks pretty good. Then I attached the ground wire to the profiles and secured the cable to the 1-3 bolt with a zip tie. This will prevent the cable from pulling on the power supply. After all of this, I also mounted our PET strip holder spool to the machine body like this. Okay, everything seems correct. Now I'm attaching our circuit to the circuit cover, and then we can continue with modifying the hot end. Our filament needs to be somewhere around 1.75 mm, so I drilled one of my nozzles to be close to that using a 1 mm drill bit. I also drilled a 4 mm hole in the hot end's body and slightly enlarged the nozzle's mounting hole. Now I am putting everything back onto the hot end. As you can see, I also cut the cables a little shorter and added connectors to their ends. I am mounting our hot end like this onto the Sigma profiles using an angle bracket. This way heat cannot travel to the body, so no heat is wasted and we can better control the temperature. We have an end switch input on the PCB, but I decided not to use one, because while testing the device, I found it unreliable for detecting the PET strips. And now we are almost done. The only thing left is uploading the code. Let me briefly explain how it works. First of all, yes, the code is a bit of a spaghetti mix, but it works. So let's go through it quickly. The first part is the menu library. It handles the basic menu functions like drawing the main screen and navigating through options. You probably won't need to change anything here. Next is the thermistor library. This is where we read the thermistor using the Steinhardt formula. Why? Because thermistors are non-linear. As the temperature increases, their resistance drops faster. So we need to calculate the actual temperature from the ADC reading of the voltage divider. The most important parameter here is the beta value. I used 3950 because most thermistors used in the 3D printers are rated at this value. As you can see, I set my soldering iron to 260 degrees and the STM32 shows nearly the same result. So it is accurate in my case. After that, there is the buzzer library. It is simply a collection of buzzer melodies, nothing more. Now the two most important libraries. First, the ST7789 library, which we use to communicate with the display. This library was created by these guys, link in the description. And for the PID control, we are using this library created by this person, also link in the description. In the main section, we have some defines. The important ones are the values that the STM32 starts with after a power cycle. We also have a rotary encoder logic and stepper motor control, which simply generates a PWM signal. When the PWM frequency is low, the motor turns slowly. When it's high, the motor turns faster. There is also a soft start function, so it begins slowly and then ramps up. Now let's talk about the PID values. These work great for me, but I had to try many combinations to get them right. If they are wrong, the heater temperature will overshoot or oscillate. Kp is based on error. If it's too high, the temperature will rise quickly and overshoot. If it's too low, the heater may never reach target temperature. Ki fixes the steady state error. For example, if the temperature reaches 255 degrees and stays there while the target is 260 degrees, Ki will push it up slowly, but if Ki is too high, you will get oscillations. Kd helps when the temperature is rising or falling too quickly. It's useful for reducing overshoot. Just lower the Kp and increase Kd slightly. All of these values work together to calculate the PWM duty cycle, which determines the heater power. It continuously adjusts itself based on the thermistor reading. Inside the while loop, there are many if this happens, do that checks. Nothing too special, so let's upload the code. For uploading, I've already created a hex file, so you don't need to open CubeIDE. Just open STM32, ST-Link utility, connect your ST-Link to the board, and flash the hex file. Super simple. Now let's continue assembling the rest of the machine. I assembled the circuit cover like this and put these covers here, so cables are no longer visible for a cleaner look. I also printed another piece to cover this part, just apply a little glue to secure it. For the last part, you can see I crimped a ring connector to the one end of this cable and a pin connector to the other. I'm using this part of a terminal block to screw one side of it like this, and on the other side of the terminal block we will be screwing our filament. Then we attach it like this to our geared spool. It seems we are done, so let's cut our PET bottle. I'm using a 5-liter bottle for this. We need to get rid of these grooves on the outside. So first I fill it with some water and start heating it on my electric stove. This puts a little pressure inside the bottle and keeps it from burning. I just hold it above the stove and as you can see, it slowly becomes smoother and smoother. When we are finished, it should look something like this. Next, we clean it with isopropyl alcohol or nail polish remover. After drying the inside, we cut the bottle into a single strip using a tool made by this person. Link in the description. In my case, the strip comes out at 8.4mm wide and stays pretty consistent along its length. After that, we end up with a long strip. We need to wind it onto a spool, otherwise it will tangle while we are making the filament. And as you can see, once it's spooled, it looks pretty neat. Now let's get into the machine. I want to simply explain the menu. As we first open the machine, you can see the target temperature, the measured temperature, and the speed. To change any of these, we simply go down to settings and adjust them from there. We can also turn the buzzer on or off as well as the end switch. Mine is off because we are not using one. Then we can return to the main menu. First, we need to preheat the device before starting. So let's click preheat and now it is heating. Next, we pass our PET strip into the machine using pliers. Just like that, we have reached the target temperature. I pull a bit of filament out, attach it to the terminal block and tighten it with pliers. Now we can finally start the machine. Just click start and here we go. It's a bit slow, but that's completely normal for PET-to-Filament machines like this. I fast forwarded a bit and as you can see we got plenty of filament. 9.5 meters to be exact, from a 5-liter bottle. I actually spool it like this to keep it tidy and honestly it looks pretty cool. In my case, the filament came out around 1.9mm, which is a little thicker than typical filament, but the middle is hollow, so the density is more or less the same. The important thing is that it has to fit into the 3D printer's hot end. And in my case, it does. For some reason, the filament decided to unspool itself, and at that point I just accepted my fate and left it like that. Now let's print something to see if it's any good. I set my hot end temperature to 280 degrees, but you need to be really careful here, because hot ends with PTFE tubes, aka Teflon tubes, can be dangerous above 260 degrees. Mine is a bimetal hot end, so we are fine. Here you can see some of my prints. In the first two, I had a bit of under extrusion, so I increased the flow multiplier by 20%. That fixed it and the print came out great. Then I found the perfect sweet spot, 300 degrees with 15% more flow, and waste mode looked like this.
This is pure glass. You're a goddamn artist.
Actually, it's just basic engineering, but thank you, Jesse. I'm glad it's acceptable. Now I want to mention some important things. First of all, our STM32 has 64 KB of memory, and we are nearly using all of it, so there is no space left for thermal runaway protection. If you want to make this project, please do it at your own risk. I'm sharing all the SolidWorks files, STL files, CubeIDE files, and KiCad files with you, along with all the parts you need to buy and the tools you need, all in the video description. That's it for this video. Hopefully you liked it. If so, don't forget to like, share and subscribe, and I will be waiting your thoughts in the comments down below. Take care and see you soon.